Okay, so welcome back. Our second speaker today is Professor Rekha Santhanam from IIT Bombay. Rekha will be speaking on model categories.
All right. Hi, everyone. I hope I'm audible. Um, all right. So I'll be talking about model categories today, and some of these things were alluded to by both Samik and in Shamik's talk, I think somewhat in Somnath's talk, and also in Shrikant's talk. Okay. So one of the things that, so if I just talk about the category of topological spaces, so please let me know if this font is big enough when I write, and I have to start writing a bit slower. Okay. So for topological spaces, we want to really study them. We want to study topological spaces up to homotopy. Okay, we want to study them up to homotopy. Which means that if two spaces are homotopy equivalent, we don't really want to be distinguishing between them. All right. So one thing we can always do is so if this is my category of topological spaces, so maps are continuous functions. All right. Then what I can always do is, what we call the naive homotopy category. Would be that we take the objects of naive homotopy category of topological spaces. Would be for me the category whose objects are same as or let me just say topological spaces, and morphisms between x and y are given by you take the homotopy classes of maps. So remember, these are all continuous functions from x to y modded out up to homotopy equivalences. Okay, and this works fine. But often actually to check if two things are homotopy equivalent is much harder. And usually when we are talking about the category of, so we usually want to study topological spaces up to what we call weak homotopy equivalences. Okay, so since we want to study them up to weak homotopy equivalences, now we don't have maps going back and forth, unlike in the case, so remember this is an what is a weak homotopy equivalence? X to Y is a weak homotopy equivalence if and only if for all the homotopy groups induce isomorphism between at all levels. Okay, so there's an isomorphism of homotopy groups. But this doesn't really give you a map. There is no map back. Okay, so we cannot talk about the homotopy category in this sense. Another example we can study, which has a similar situation is something that, so this was one situation where I might care for something different. The other situation that Shrikant talked about yesterday was when you talk about chain complexes. So these are chain complexes of R modules. And remember, so any such chain complex comes with a, so you have this differentials along with them. And then morphisms are morphisms between two such chain complexes has to commute with the differentials, right? So if I have, so if my FK, these collection of morphisms are there, then they have to commute. Okay. So these are my morphisms. Then given such morphisms, what now there are two ways. So one thing is that you may want to study, so we can study chain complexes up to chain homotopy equivalences, which Shrikant talked about yesterday. And in this case, I can talk about this category where, so I'm not writing this just because I want to use them. So I can talk about the homotopy category of CHR, where I'll just take objects as these chain complexes. So, and just for completeness, I should say R is an associative ring, which I should have mentioned. Objects and morphisms are, so morphisms between any two chains M and N is all the, so I don't, in morphisms of chain complexes modded out up to chain homotopy equivalences. All right. So, but on the other hand, we may, often we want to study them instead. Often we want to study this category up to what are called quasi isomorphisms. I think this also Shrikant mentioned, but let me define it again. So what is a quasi isomorphism of chain complexes? That is maps which induce isomorphisms on homology. Okay. Again, I don't really have a notion of homotopy equivalences. There are no map. I mean, there is not a map going the other way. Okay, so this is an isomorphism on the homology level, not on the level of the chain complexes themselves. There is no map back, so to say. So it's much harder to say what I'm. So in either of these cases, so then now this kind of connects to the kind of things that Somnath was talking about. What I really want to do is say I want to localize. So in my example, either localize the category of topological spaces up with respect to weak homotopy equivalences. So this is one example. So one, I don't know, maybe example is not the correct word. So these are a couple of things we want to be able to do. So maybe I should just put 1 and 2 here and then kind of generalize it. Say, suppose I want to localize chain, the category of chain complexes to the category CHR up to quasi isomorphisms. Okay, there are different categorical methods one may want to use. So there are various issues. One runs into like you need your category to be small, which means the objects have to be the class of objects has to form a set, or after doing the localization, you want to end up with the ordinary category and not be in a situation where the Hom sets turn out to be, I mean, not sets anymore and classes instead. So, so one solution to this question is, so one solution to this problem is offered by constructing what are called model categories. But model category is much richer than that, and I'll tell you why in a bit. But this is one motivation I'm just offering as a start off. Okay, so so without much further ado, let me actually define what a model category is. So what is a model category? So definition. A model category is a category N with 3 distinguished classes of morphisms called weak equivalences, cofibrations. So these names should sound familiar. So they are all actually coming from something, and fibrations. Okay. But formally, I'm just saying I'm going to define a class of morphisms as weak equivalences, a class as cofibrations, another class as fibrations. Okay. So we can denote this as W, this as C, and this as F. Okay, so these are 3 classes of morphisms in here, satisfying the following axioms. So often yeah. So I'll tell you, so I could have avoided writing the axioms, but it's good to see it at least once if you've not seen them before. So one thing, so sometimes people assume all colimits and all limits exist. For now, I'll just assume finite limits and colimits exist, but you can ask for more. Okay. The important thing is that if if um, if 2 out of F, G, and Fg, so these are composition of morphisms, belong to weak equivalences, then this will imply the third one belongs to omega, weak equivalences also. So it's saying that if if F and G are weak equivalences, so is its composition. If the composition and one of the morphisms is a weak equivalence, then the third one also has to be, and the second one also has to be. All right. Then we have a condition which says that retracts of cofibrations should be cofibrations, and so all so this one I just don't want to get into too much because or maybe I will talk about it. So let me just, so I'll just write this, and maybe later if there are questions I can say all the classes are preserved under retracts. The more interesting axioms, which you would have noticed that Samik talked about, one of them is called the weak factorization theorem and the weak factorization axiom, and the other one is about the other one is lifting statements. So the lifting axiom basically says that if, so let me draw a diagram of this kind. So I will call this I, and this is P, and the corresponding things can be anything. They don't play a role. But if the dotted arrow exists, if I is a cofibration and P is both a cofibration and a weak equivalence. So this is one. Similarly, the dotted arrow will also exist. So basically just saying that there is a lifting map like this. If I is a cofibration and a weak equivalence, and P is a fibration. Sorry, I think. Sorry. Okay. And lastly, finally, I want to say that given any map f from x to y in M, uh, it can be factored as a map I in, so what are called acyclic fibrations, so cofibrations, so something which is a weak equivalence and a cofibration. Or we could also we can factorize it as a map where this map belongs to this map is a acyclic fibrations, that is, it's a weak equivalence and a fibration, and this map is just a fibration, cofibration. Okay. Okay, so these are so if you remember when Samik was talking about this mapping cylinder and the path space, he was talking about how to factorize any given map into a cofibration and a weak equivalence and things and fibration, etc. So this is where these ideas come from. So before I actually give you some examples, let me just state a couple of immediate consequences. So one consequence is that all fibrations have a right lift, so or rather that they have right lifting property is clear, but a map, a morphism is a fibration, morphism in M is a fibration if and only if it has right lifting property with respect to all acyclic cofibrations. So by that I mean something which is cofibration plus weak equivalence. Okay, and similarly a morphism is, so I have the dual thing, a morphism is a cofibration if and only if it has left lifting property with respect to acyclic, with respect to all acyclic fibrations. So that is fibration plus weak equivalence. So notice what this means is that in a model category, really you only have control on one, you have control on the weak equivalences and fibrations, or you have control over the cofibrations and the weak equivalences. Okay, so this should answer, I think, one of the questions Vignesh had last time. So basically, you know one or the other. So if I tell you what the fibrations are and what the weak equivalences are, they completely determine the cofibrations and vice versa. Right? I mean, up to at least these lifting properties. So what does all this structure allow you to do? Okay, so all this setup basically allows me to define what is called the homotopy category. So it allows me to define it formally, and so this setup allows us to define a notion of homotopy in tune with the weak equivalences. Okay, and without actually define anything, I'm just telling you that there is, like, I can define a homotopy category of M where objects are objects of M and morphisms are so morphisms between x, y are given by some appropriate replacements of x and y, and then homotopy classes between them. Okay, so I know I'm not telling you what any of these things actually mean, but let me just first tell you that this would be a useful setup. It will let me invert exactly the things I want. And now let me give you the examples that look familiar. So let me first start with topological spaces. And let me first try to study topological spaces with where the weak equivalences are, so instead of using the word weak equivalences, let me use W is a set of, classes of homotopy. This will consist of all homotopy equivalences. So we'll say something is in this class if it is a homotopy equivalence. Okay, so fibration here okay, sorry, I should have said one more thing. So let me just erase this and say that because otherwise what I just said is so why is this useful? That is something I should have said. So this is useful because this is precisely do what we want it to do. So notice I will have a functor from this to this category. Okay, and if I'm given any functor to some category D, so this is some category and this is some functor F, and if this takes if this F takes weak equivalences here, two isomorphisms in D, then it turns out it will always factor through the homotopy category. Okay, so in that sense, homotopy category will be the universal thing which inverts these weak equivalences. All right, so in that sense, it's doing exactly the thing we want. Okay, so before we delve into any formal definitions, let's now actually do a couple of examples. So now let me talk about topological spaces, where my class of weak equivalences is given by homotopy equivalences. So a morphism is considered to be a weak equivalence if it's a homotopy equivalence. A morphism is given to be fibration if it has, so I'll say something is a fibration, F belongs to F, if it has homotopy lifting property with respect to all spaces. So this is something Samik talked about last time. These are called Hurewicz fibrations. All right, so I have a lifting. So if I have a diagram which commutes like this, and if I had a homotopy to Y, if this lifts, then this is called a Hurewicz. So this is a fibration. It's called a Hurewicz fibration. So Samik talked about how and the cofibrations were supposed to be elements with okay. So cofibrations were supposed to be these elements, these morphisms, which have so ideally dually you want to think that if, or let me use something else, let me use I. If it has homotopy extension property. This is also something Samik mentioned, so I can write it down in a second. Plus, it must be a closed inclusion. Okay, so this is something needed to make this into a model structure. Okay. Because you also need things to lift against each other. All right, so the factorization is something that Samik talked about. Just to recall, what was homotopy extension property? That so I can write it like a diagram. Okay, so suppose I have a diagram where Let's see. So I'm trying to crush it into very small space, but let me see if this works. Suppose I had a diagram of this form. Uh, okay, sorry, I think I. So suppose I had maps like this, okay? So then the claim is that even this will extend. Okay, so this is something. So having this dotted arrow is homotopy extension property. So I can extend homotopies on A to homotopies on B, right? As long as the initial map was the same. Okay. So it was so Storm proved that this defines a model category. So you have to prove all these 5 axioms. And this the homotopy category matches with what we wanted before. So the homotopy category is equivalent to what we call the naive homotopy category earlier, that it's exactly the category in which all the homotopy equivalences are inverted. All right. So okay, this is same as naive homotopy category. Okay, I think I can go maybe a little faster now. All right, so but this is not the real category we want to work with. It matches with what we know already. So remember, some of the things that Samik has done should help you kind of see how the how the factorization comes and things like that. So an alternate model that we really want to use all the time on topological spaces is we really want weak equivalences, to be weak homotopy equivalences, which we mentioned before. So in this situation, what we need is the fibrations have to be what are called the serif fibrations. So I think people would have come across this. Basically, that means that something is a serif fibration if it lifts against so you take any disk and you take dn cross I, then there should be a lift. So for all n, okay, instead of asking it to lift homotopies for all, it having homotopy lifting property with respect to all A, all spaces A, we are saying it should have a homotopy lifting property with respect to all disks. Okay, so I hope this is, I'm assuming this is standard notation, but let me just. Now, so since I'm writing this, I should also write this. Okay. So, and in this case, it turns out the cofibrations are going to be all possible retracts of generalized CW complexes. So if you remember, CW complexes are the objects that we like working with. So by saying generalized CW complexes, it just means that there is no restriction on when we add a cell of dimension n, we are allowed to add cells of dimension n at uh, in any order, like they don't have to be in a particular order. Okay, not like raising dimension every time. All right. So it turns out that this forms a model, this forms a model category. And this is the one we would like to work with when we do topologic model category. And this is the one we like to work with when we do when we work with topological spaces. And the nice thing about it is that in this homotopy category, okay, in this homotopy category of topological spaces, if I look at maps from A to X, where A is a CW complex, it's in bijection with the set of maps, homotopy classes of maps from A to X. All right, and in this model, every space will be homotopy equivalent to a CW complex, or weakly equivalent to a CW complex, which is the structure we want to work with all the time, right? Uh, this also has some extra structure, which maybe I'll mention later if I have time. But now let me quickly just mention the example of the chain complexes. If I took quasi isomorphisms, how do I don't know if I labeled this anything, but this is my third example that I'm talking about. So if I take weak equivalences to be quasi isomorphisms here, like we wanted to before, and we take cofibrations to be monomorphisms whose co-kernel has to be a all of these are projective are modules, and fibrations are just epimorphisms. So then together with these choices, this is a model category. And this actually gives as a, its homotopy category is equivalent to the category of projective R modules. Chain complexes of projective R modules. Up to modded out by chain homotopy equivalences. All right, so these give me familiar settings that I know something about. All right, so that should explain why I care about model categories per se. All right. So this is one reasoning behind talking about model categories. So I said that it has a much richer structure, and then there's more to it than just this. So I can now tell you what is so special about doing this also. So they also have this slightly richer notion, which is useful, often useful. So notice one thing in topological spaces that if I take a push out of a diagram like this, where I take the n-1 sphere, I take the map to a singleton set, then if I take a push out of this diagram, this should just give me a point. All right. But a homotopy equivalent diagram to this is the following one. This is quite the standard example where notice dn is something which is contractible, so it is homotopy equivalent here. I'm not changing anything. But when I take a push out of this diagram, I get a sphere which is definitely not, definitely the point, singleton point is not homotopic to this, right? So in general, push-outs do not, or like push-outs or pullbacks or any limits, push-outs do not preserve weak equivalences or weak equivalences of diagrams. So if I have in a model category setup, I can actually define, we can formally define what we call homotopy colimits and limits. Or homotopy limits, which are preserved under diagrams, equivalent, weakly equivalent diagrams. And one of the things I need for this is this notion of fibrant replacement and cofibrant replacement. So let me just quickly say that. So if X is a space, all right, so X is any space, then sorry, not space. So I should start with a model category. So let M be a model category with phi as initial object and star as the final object. So initial object in the sense that there is always going to be a morphism from phi to any space in X. And remember, I can always factor this through a cofibration and then a weak equivalence. All right. So this will then, so this X prime is called a cofibrant replacement. And similarly, if I take X to a point and then I factor it, so this is a weak equivalence to some X prime. So maybe I'll use the standard notation here. So this is called the cofibrant replacement. So it is denoted like this. So there is a C put here. And similarly, I have something called a fibrant replacement with a F put here, where this map now becomes a fibration. And XF is called a cofibrant, I'm sorry, a fibrant replacement. And notice so this is the notation I had used earlier. So if you recall, I said that in the homotopy category, the morphisms from X to Y. So there is a notion of homotopy equivalence that we can define because you're allowed to define something which is called like a cylinder object. And what you then, this is defined to be, so you're supposed to take a fibrant cofibrant replacement of something and then again cofibrant replacement of something, and you're supposed to take the homotopy classes of maps for them. All right, so this is the sort of setup, and in general what we are also allowed to do is, so in so what I wanted to say is that a similar sort of thing allows me so in a model category, if it happens that I have a diagram from X to Y to Z where both these maps are cofibrations, so this is a cofibration, this is a cofibration, and this happens to be cofibrant, then when I take its honest push out, so this push out will be preserved under homotopy equivalence of diagrams, or sorry, equivalent weakly equivalent diagrams. All right. So it's useful often to be able to make constructions of, so there can be precise definitions one can write down if one has a good way to write down the cofibrant replacement of something. So if you're given a diagram where you have, sorry, I think I wrote the diagram the other way around. So if I have X mapping to Y and X mapping to Z. So given such a diagram, one is able to actually construct a homotopy push out of this diagram, by which we mean that we can write down something which will get preserved under weakly equivalent such diagrams. All right. So any other weakly equivalent diagram to this will also have a weakly equivalent push out, right? And Okay. Um, yes. Okay, so that is one aspect. So that is one other use that is useful. And then finally, I just want to mention that the thing that we head towards next time is that once you have built this theory, and if you have another category, which is also a model category, you may want to compare them. And more importantly, for instance, so we will do this next time. But given any two model categories, you can talk about what is called a Quillen pair um, of model categories. So, so this is just an adjoint pair of functors. So I have M is a model category and N is a model category. Then I have an adjoint pair, L and R, a left adjoint and a right adjoint. So remember what an adjoint pair means, that so there is a natural isomorphism between so, so from morphisms of X to Ry is isomorphic to morphisms between Lx to Y, where so X is the object of M and Y is the object of N. All right. So there is an isomorphism like this. If L preserves cofibrations and acyclic cofibrations, then this is called a Quillen pair. Similarly, or if R preserves fibrations and acyclic fibrations. Okay, the point is whenever I have a Quillen pair, then I can talk about something called Quillen equivalence. And the advantage of this setup then is that so first of all, having this basically means that I end up getting an adjoint pair on the homotopy category. Okay, so this induces a adjoint pair. And further, if it is a Quillen equivalence, if LR give a Quillen equivalence, and I'll tell you what it is in a second. So this just means that if X to Ry is a weak equivalence, or like, sorry. So notice I can go from X to, I should make sure my direction is correct. One second. So if it is Ry, then I think I have, if this is a weak equivalence, and so is I'm just making sure I got my maps in the correct direction. All right, if these are weak equivalences. Okay, so this, I mean, I can make it much more specific. So, but the point is this will induces, so this induces a equivalence of homotopy categories. So if you happen, for instance, in the example of topological spaces, if I'm working with topological spaces, what we'll talk about next time is we'll talk about the category of simplicial sets, and we'll try to at least give an idea about how the category, doing homotopy theory in the category of simplicial sets is same as doing the is same as doing homotopy theory in the category of topological spaces. Okay, and this notion of model category and the homotopy category basically lets us go back and forth between models with the same homotopy theory depending on what we want to do. So sometimes it's better to work with what are called simplicial sets, and sometimes it's better to work with topological spaces. Yeah, maybe we'll try to give examples about when is one better than the other. But one can think of simplicial sets as some combinatorial sort of data as compared to topological spaces. So I think I'll stop here if there are any questions.
So Rekha, I think there's one question in the chat if you want to take it.
So can Akshadweep tell me which example he was talking about? Is he still here? Akashdeep, sorry, I read it wrong.
I think he was talking the one where you gave the second model structure on the topological spaces.
In that one? Okay, so there the cofibrations. Oh, did I forget to write them down? No, I wrote them. So they turn out to be retracts of some maps which are retracts of generalized CW complex. So something is a so people know retracts of spaces, but they may not have thought about retracts of spaces. So functions. Okay, so you may have some maps like this. Yeah. So these are retract maps by themselves, and then you have morphisms like this. So if I have a so this morphism G is said to be a retract of F, where all this now commutes. All right, so G is a retract of F. So generalized CW complexes would be a map, would be a relative CW complexes, but map of relative CW complexes, but it's generalized in the sense that I'm not, we are allowed to go in any order. We are not going one dimension higher every time, sort of a thing when we add cells.
There's one more question by Parthapratim Ghosh, and there's a comment by Shurujit.
What about the equivalence? I think maybe I need them to be fibrant between cofibrant objects or fibrant objects. Is that what you're? Surajit, what was your comment? Maybe he's not here. Okay, so maybe this has to be for fibrant, I think for all fibrant, cofibrant objects, but I will correct it in the slides if that is an issue. But I will fix that later in the slides.
Any more questions?
And homotopy of M is a category of fractions, I believe.
What do you mean by category of fractions?
It's almost the same description that you gave. You select a class of morphisms and you want it to make it invertible.
So here it's on a set. So I said like I'm taking functions from x to phi and modding out by. So I'm doing this on the Hom of x phi, right? Sorry, where did that?
Yes. No. When you said what is HO of M, you said that whenever your weak equivalences get to an isomorphism, there is a unique functor from HOM to that category.
Yeah.
So that means HOM is the universal construct via fraction, by the method of fractions. So is it that what you mean?
No, so I mean that the construction of, I mean, I never gave a formal construction of what the homotopy category looks like. I said that it is given by these, and I mean, this is an actual set. So I don't think I'm like by fractions. Do you mean like taking a map of zigzags and?
No, not exactly. You take the path category over M, and then you introduce further morphisms corresponding to that class which you want to invert, and suitable equations, and then you get the quotient category as the category of fractions.
Okay, so I'm not modding out at the level of the category. I'm saying that I can actually, so I'm taking some class of maps at the level of, so this is a set, and then I'm modding it out by some equivalence classes. So I'm saying that this is precisely the advantage of doing model categories.
Yeah.
Okay.
If I might add, like I think calculus, this fraction, what he was talking about is like localizing at weak equivalences, and there are some technical issues if you don't have your category to be small. I think that's the precise benefit of going through this.
Yeah, so that's what I was pointing out initially, that if I try to localize at the level of the category itself, it's not an easy thing to do. So if I have this model structure, then I can actually precisely say what the morphism set looks like. I mean, I can do it without any categorical issues.
Yeah.
But of course, all the work is in gone, and like showing something is a model structure, has a model structure. Yeah. Sorry.
Yeah, but you can do it for small categories.
Yes, but for instance, topological spaces is not a small category, I think. So.
Okay, it depends on how you define your smallness. Okay, if you include
okay, so
one
there
more,
is something like essentially small.
Yeah.
So I mean, it has issues. So this is a nice
okay.
way to do it. Is the point?
Okay.
Yeah.
Hi, I have a question, Rekha.
Yeah.
So you said in between something like the model category structure is richer than I think the homotopy category or something to that effect, right?
No, there's more to it than just this localizing bit is all I meant. Like,
okay,
there is more I can do with it is all I'm saying.
You were illustrating that you can construct homotopy pushouts and this thing. Was that the point?
Yeah,
Why it's
yeah.
richer?
That was the point. Sorry if I didn't get through on that. Yeah.
Okay.
I mean, there could be other reasons why you want to work with model categories. But this was one.
I have another question.
Yes.
Yeah. So this is related to what Shrikant was doing yesterday. So there is that example of semi-projectives and so on, which sort of sits into this framework, right? Whatever you're doing.
Yeah. So I just realized from something he mentioned that I should say that I'm doing only positively graded chain complexes here. So my chain complexes are all only in the positive degrees. There is nothing in the negative degrees. But anyway, what was your question?
Yeah. In that setup, he talked about some things like thick of the category and so on, right?
Yeah.
So how does it feature here in this general setup? What is
I
it?
think this you may have to address him because I am not. I'm not so conversant with.
I guess the point is that some homotopy categories have so this concept of a thick subcategory and so on, you have to work, you need triangulations, right? I'm talking about triangulated structure on the homotopy category. And most of these homotopy categories you construct do carry a structure of a triangulated category. And so you can talk of those concepts in that generality. I don't know if that's what you were asking or you had a more specific question.
No, I mean, basically you said, I think that the thick objects are the small objects, right? And small objects is a more general.
No, that's only if you start thick subcategory generated by the ring.
Okay. Oh.
Not only one. Yeah. That's was only for the ring.
Oh, okay. Thanks.
So tomorrow, maybe in my lectures, I'll do some more examples of these thick subcategories. Somebody else also asked. So then you'll see that it's only the small, or it's only when you start with the compact object that that you start with the ring that you get small objects. Otherwise you won't.
Thanks.
It's like starting with finite CW complexes in this topological context.
So I think here I just have to add that this is true for all cofibrant objects, and so either one or the other you can check, or this is true for all fibrant objects. But I'll make these things precise next time when I'm talking about adjunctions. So I just wanted to allude that this is how you would compare different homotopy categories.
So if there are no other questions, Rekha, should we break into rooms?